Chapter 4, Discrete Random Variables. 4.2, Probability Distributions for Discrete Random Variables. The probability distribution of a discrete random variable is a graph, a table, or a formula that specifies the probability associated with each possible value that the random variable can assume. So that sounds way more complicated than it is, and hopefully by the end of this video you'll see that it sounds very fancy, but it's really not that fancy. It's the idea that if we have, let's say, the number of times that somebody's been married, and we have a data set of all the people in the United States, let's say, all the people over the age of 30, and we just are looking at how many times for each person they've been married, right? We would have, here's this person. Here's Tommy. Tommy's been married 2 times. Here's Linda. Linda's been married 1 time. Lisa's been married 2 times. Here's Lisa. Lisa has shorter hair. All right. And then we have, like, let's say millions and millions of observations. Okay. All we're doing is just tracking how often 0 happens, how often 1 happens, how often 2 happens, how often 3 happens, and we're just writing it in a convenient form. Okay. So basically that's all we're doing with this section here and with discrete probability distributions. All right, so here are the requirements for the probability distribution of a random variable x. It sounds, here they are. They're the same. They're very simple, but they're similar. The same thing as what we saw in chapter 3. All right. Here's number 1. The probabilities have to be positive, so at least 0 for each of the values of x. And then number 2 is when you add all the probabilities together, you have to get 1. Those are the requirements for a probability distribution. All right, so let's just start with an example. Let's jump into it, look at an example here. All right. As the Halloween HOA statistician, Danny was charged with, all right, that means I wasn't charged with a crime. I was charged with, that's a business term, I think. HOA likes that term, for telling somebody to do something, all right? I had to create a probability distribution reflecting the number of pieces of candy given out by each house in our neighborhood, all right? So that's where the HOA money is going. Homeowners Association money is going there, all right? Using historical data, this is true, from 1980 to present, he sought out to create an accurate probability model, giving an answer to the age-old question. Here is the question. What are the chances when you knock on a door at Halloween, you pick a house at random, right? It's not fully at random, of course, because the lights are out, you're not going to knock on the door, right? But what is the probability that they give at least 1 piece of candy? All right, so each house can give either 0 pieces of candy, 1 piece of candy, or 2 pieces of candy. All right, the HOA banned in 1985 the ability for houses to give out anything more than 2 pieces of candy. 2 is the most. So 0 or 1 or 2. All right, so let's select a house at random, knock on the door. What is the probability they give out at least 1 piece of candy? All right, so what we're tracking here is the behavior of the random variable x, where x is discrete data, which represents the number of pieces of candy for a single house, how much they give out. All right, so x equals the number of pieces of candy. All right, so in our example here, x has to take on a value that's either 0 or 1 or 2. Those are the only possible outcomes, so this is discrete data. All right, so now the data set I used, I emphasize here that I'm using historical data in this particular problem. Okay, here's the historical data. All right, this is my data set right here. I gave the house a random ID. Okay, but this is all the houses in the neighborhood. It's a big neighborhood. There's 1,000 houses total. So there's 1,000 experimental units, let's say here. Okay, 1,000 observations. Okay, Old Man Withers gets their own ID. Okay, but what I have is for each data point, each value of the experimental unit in this case, all right, I have the number of pieces of candy right there. Those correspond to each individual house. So all I want to do is create, now if you think back to chapter 2, right, that final exam question from that course I got fired from teaching, right, the organizational tool solution to our organizational problem. We have a raw data set. We got to create a frequency distribution, which is really all, from an empirical approach, that's really all a probability distribution is doing for us, a discrete probability distribution. All right, so I went into StatCrunch and I created a frequency distribution, and here it is. 0 happened 300 times out of 1,000, so that happens 30% of the time. 1 happened 600 times, so that happened 60% of the time. And 2 happened 100 times out of 1,000, so that happened 10% of the time. All right? Can you see the probability distribution here? We have each x value and the corresponding probability that's associated with it. Right? Each one of these probabilities is positive. And when we add them all up, we get 1. So it's a valid probability distribution. All right? And this is what it looks like. I made it nice and Halloween color. All right? That's the probability distribution. X equals 0 or 1 or 2. That's it. What about 3? I mean, we could put 3 there, but 3 happens with 0 probability. Okay? So this probability distribution is describing a real-world data set in this particular case. Okay? So now we can answer our question. All right, what is the probability they give out at least one piece of candy when trick or treat, right? That's written this way. All right, so I'm going to focus here a bit on the symbols, drag my feet a bit, all right, because these symbols are going to be important to us as we move through the course, all right? The idea of having an inequality symbol, all right? These are equality symbols right here. That's the probability x equals 1. This is the probability x equals 2, all right? But this is an inequality symbol, which represents 1 or more. So 1 or more, that's this probability plus this probability, okay? So it's the probability that at x equals 1, that's listed right there, that's 0.6, and it's the probability at x equals 2, that's listed right there, that's 0.1. That's the point of a probability distribution, all right? It makes our life a little bit easier than digging through a whole data set of 1,000 observations, okay? Now, x equals 1 and x equals 2, those by definition are mutually exclusive, okay? You can't have a house that gives out both 1 and 2 pieces of candy at the same time, okay? This isn't quantum mechanics or something more something complex, all right? So pretty clear. It has to be either A or B. That means all we have to do to find the probability of A or B, which is what this really means, probability x is at least 1, means the probability of 1 or 2. So it's the probability at 1 plus probability at 2. We don't have to subtract off any intersection or overlap because these are mutually exclusive events, all right? So long story short here, all right, we got to be clear. We got to be clear on understanding this inequality notation. That's at least 1, so 1 or more. So I'm going to include that in my probability calculation. All right, so that equals 0.6 plus 0.1. Hopefully I haven't fallen asleep. I'm dragging my feet here intentionally on this problem because I know that we're going to need this notation in chapter 5, 6, 7, so on and so forth. Okay, so probability x is at least 1, that equals 0.7. How about if we're looking at the discrete probability distribution for flipping a fair coin one time and counting the number of heads? Okay, so right now, if I had everybody that's watching this video, all 14 of you, I had you each flip a coin one time, and I wanted you to report back to me on how many heads you got. That's x equals the number of heads. Everybody would have to report back to me either 0 or 1. And then what probabilities are associated with those. That's an argument we made in chapter 3 that getting heads and tails are equally likely. So basically by definition here, we'd say that the probability x equals 0 is 0.5. The probability x equals 1 is 0.5. So this is 0 heads. That's no heads. That's no heads. That's 1 head or 1 heads. Okay, each has probability of 0.5, and notice again that our rules for probability distributions, all right, they're satisfied. All right, what about if we flipped 2 heads? Okay, what if we flipped 2 heads? Now let's actually, before we create the probability distribution here, let's just list out the sample points. All right, the sample space here. Let's see here. If we're counting the number of heads, we're flipping 2 coins. Okay, we could get 2 heads. That would be head head. Right? We could get 1 head, so that could happen with heads on one and tails on the other, or we could get tails on the first one and heads on the other one, right? Or we could get 2 tails. Those are our sample points, right? Okay, so we're counting the number of heads. We're counting the number of heads here, okay? So how many heads do we have here? The answer is 2. How many heads do we have here? The answer is 1. 1 here. And how many heads do we have here? The answer is 0. We can get 0 heads or 1 head or 2 heads. How many ways can we get 0 heads? The answer is 1. 1 out of 4, right? How many ways can we get 1 head? The answer is 1. Excuse me, 2. 2 ways, right? 2 ways. Sorry. 2 ways we can get exactly 1, and there's 1 way we can get exactly 2, all right? So the probability of getting 2 heads is 1 out of 4. Probability of getting 1 head is 1/2. The probability of getting no heads is 1 out of 4. All right, so that's our probability distribution. There it is. All right, so we can get 0 or 1 or 2, and each of those have corresponding probabilities. All right, let's up the stakes a little bit. How about if we flip a coin 3 times and count the number of heads? All right, so we could get all 3 heads. So here our sample space could be all 3 heads. Let's see if we can get this in there. All heads. We could get, how about head? If we have 2 heads, we could get head, tail, head, tail, head, head, and we could get head, head, tail. All right, so this would be 3 heads. We could get 2 heads, which could occur in that way, right? We could get 1 head, so tail, head, tail, head, tail, 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 head. Or we could get all tails. All right. This right here represents 1 head, and then this represents 0 heads, right? So 0 heads can happen 1 way, so 1 out of 8 total in the sample space, right? And so on and so forth. So what we can see is that 0 happens with this probability, all right? 0 happens with a probability of 0.125, which is 1 out of 8, right? This right here is 3 out of 8. This right here is 3 out of 8, and this right here is 1 out of 8, right? Which we can derive in a classical probability sense, which we briefly looked at in chapter 3, right here. All right. So the idea here with this probability distribution is we don't want to, if we don't have to, create this probability distribution from scratch. And we don't want to have to deal with looking at the empirical data. We just want to analyze the probability distribution as given. All right, so what is the probability of exactly 2 heads? So we can use our probability distribution here and answer that question. Really not too bad once we have the probability distribution written. All right, so what's the probability of at least 2 heads? We can go back here and look at the number of favorable here being defined as having at least 2 heads, right? Excuse me, exactly 2 heads would be favorable here. Exactly 2 heads, right? That would be this one, and this one, right? Exactly 2 heads. So that would be 3 out of 8, right? Well, we can see that that's exactly what this tells us, okay? Probability x equals 2, it's written right there. It's 0.375. That's going to happen with relative frequency 0.38 or 0.375. That's what probability represents. All right, what about the probability of at least 2 heads? So here we're looking at the probability of 2 heads or 3 heads. So the probability x equals 2 or the probability x equals 3. So the probability that x, we'll say, is at least 2 equals the probability of 2 or 3, which equals the probability of 2 plus the probability of 3. All right, so the probability x is at least 2 equals the probability of 2 plus the probability of 3. All right, so all we have to do is add those probabilities together, those probabilities that are describing the sample point 2 and 3. Add those probabilities together, and what we end up getting is 0.5. What about the probability of less than 3 heads? The probability of less than 3 heads. Okay, so the key thing here is to know that if we say less than 3, if I want to have less than 3 kids, all right, it means that 3 is not a valid answer. So 3 is not included here. So saying the probability of less than 3 heads is the same thing as saying less than or equal to 2. All right, so the probability x is less than 3 is the same thing as saying the probability that x is less than or equal to 2. All right, again, all I have to do is add up the probabilities from 0 or 1 or 2. So we add all these probabilities together, and that gives us our answer, which in this case, it's 0.875. Okay, that's x is less than or equal to 2. So how do we interpret that? Well, there's 88, almost a 90% chance that if we flip 3 coins, we're going to have less than 2 heads. Excuse me, less than 3 heads. All right, 2 or fewer. All right. Thought of another way, if we have 3 kids, what's the probability that we have less than 3 girls? The answer is almost 90%. 2 or 1 or 0. All right, pop quiz before we end here. Here's the quiz. Let's say x equals the number of siblings. If somebody's selected at random, what is the probability they have at least 2 siblings? All right, now again, we can't answer this probability question. All right, we can't answer this probability question unless we have the data in some way. Here we're looking at the data in terms of a probability distribution. All right, so here's the real world data. All right, I've collected this data from students before. It's pretty reasonable. All right, it's discrete data because you can either have 0 or 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10 or 11 or 12 or 13. Right, we can keep listing them out. All right, every time we ask the student how many siblings they have, they'd answer some finite value that we could list on the number line. All right. Key thing with discrete is you're counting. The key thing with continuous is you're measuring. And the key thing as well is we're in a chapter 4 video, and chapter 4 is all about discrete random variables and discrete probability distributions. All right. So at least 2 siblings, all we have to do is add up all the probabilities at 2 plus 3 plus 4 plus 5 plus 6. I made this multiple choice here. All right, so let's see what the answer is. All right, add up 2 through 6, okay? And we end up crunching some numbers here and getting 0.45. Another way you could have answered this is to use the rule of complements, which we briefly looked at in chapter 3. And it really is only to understand and better be able to deal with probability distributions and some of the other methods in our course that we actually have a rule of complements that's important to us, okay? But note that the probability that x is less than or equal to 1 plus the probability x is greater than or equal to 2, that equals 1 by definition, okay? So we want to figure out the probability x is at least 2. So if I subtract this piece from both sides, all right, move that piece over there, all I have to do is then figure out what this piece is and subtract that from 1, which is what we can do as well. In either case, you get 0.45 as the answer to the question.